So the Zoom people, can you see that screen on your computer? Zoom people? Oh, there is no one, I guess. Okay, so what we did in last week, we started the energy equation, but before we start discussing the energy equation, we wanted to discuss some of the basis of energy equation. So we started from Euler's equation of motion, and then we discussed a little bit about Bernoulli's equation, right? And we discussed that we knew that the Bernoulli's equation is derived from the incompressible and the inviscid fluid. That means it will not be applicable for the compressible and the fluid with high viscosity. And there are some other limitations also, like there can't be any loss in the system, there can't be any addition of energy to the system. So under certain circumstances, you can use the Bernoulli's equation, right? So that's where we stopped the limitations. So what we will do today, we will try to see some of the applications of Bernoulli's equation where you can use the Bernoulli's equation and you can get the result easily. That's what we will do. And once we are done with that, we will start working on our class example 13, where you will apply the Bernoulli's equation for 2 different scenarios. Okay, so that is the plan. And I don't think I can start the EGL or HGL today, but that's okay. And you will have one homework 8 due, that is next Monday. The reason I'm telling it right now, so that you will have a kind of 1 week that will be based on your Bernoulli's equation and energy equation. Okay, so let's start working on that. We did the limitations of Bernoulli's equation. We will just add, start working on the applications of Bernoulli's equation. So one of the common application of Bernoulli's equation is you need to calculate the flow from a reservoir. Okay, so if you work as a hydraulic engineer or hydrologic engineer in any company or something, this is the very common case you will see for, like, okay, what will be the flow from the reservoir, or what will be the flow from the canal or something like that, or how can you find the total flow from a system. So you can actually apply the Bernoulli's equation unless there is a huge loss, like friction or something. So for the normal case, just like this one, we will try to apply the Bernoulli's equation to get the flow. Now, the flow is mainly Q, okay, the volumetric flow rate, and Q equals to AV, right? And there is a condition for V. V should be what? Perpendicular to the area, right? Now, calculating area is very easy if you have the dimension, right? If it's circular, if you know the diameter, you can calculate the area. If it's rectangular, if you know the width and height, you can calculate the area. So calculating area is not a problem. The problem is how you can calculate the what? The velocity, right? So that's what we will try to do if we can calculate the velocity for this system. Okay. Now, what we will do, we will try to apply the Bernoulli's equation at 2 points, like 2 points of interest, not any 2 points. And then we will try to identify the unknowns. Okay. So here, this is a reservoir. Water is coming, like no water is coming from the top. It is kind of like stagnant, and water is passing through this outlet. Okay. So A is the inlet. And B is what? Outlet. So we have one inlet, one outlet. That's great. Here. And so what we will do, since these 2 points are the points of interest, in this case, we will apply the Bernoulli's equation in between A and B. Okay. So what we will do, I will write down the Bernoulli's equation, P A rho V A square 2 G Z A. And on the other side, it will be for B, right? P B rho. Since we are using the incompressible fluid, so density will not be changed at inlet or outlet. So we can always use rho, and we don't need to define by rho A and rho B. B square over 2 G, right? That is the equation for inlet and outlet. Now, since we need to find the flow from the reservoir, there is no flow at A, so there is no point to calculate anything on A. So we need to calculate actually QB. So AB, VB, that's what we need to calculate, right? So we will try to calculate the VB. Now, point A, that is open to atmosphere. So what do you think? What will be PA? It will be 0. PB, water is discharging into open atmosphere. So what will be PB? 0. Again 0. So this whole thing is 0. Whole thing is 0 because open to atmosphere, open to atmosphere, so 0, 0, right? So 2 terms gone. Now we need to think about VA and VB. As I said, point A here, there is no flow, incoming flow here. It's just stagnant there. Okay. Also, you know VQ equals to AV, right? Here. From mass conservation, what do we know? Incoming flow equals to outgoing flow, right? So that huge amount of its water is coming out through this small hole. Obviously, the velocity will be very, very high because the area is very small, right? So VA is way, way smaller than VB. And that's why whenever we have an open reservoir, we can say the velocity at B is almost 0. It's not 0, but it's almost 0. So what I will write down, VB is almost 0 because open reservoir. Okay, yes. Oh, that should be VA. Okay. So that makes this term 0, right? I can't do anything about VB. VB is the thing we need to know. So VB equals to VB. So I'm not doing anything here. Now the next thing is G will be always 32.2 or 9.81 as long as you are in this planet. If you go to some other planet, obviously that will be different. So we don't need to worry about the Z. G, we need to worry about Z. So for Z, this is the distance from a reference point to the inlet or to the outlet, right? Now, are you seeing the word datum? Datum is the reference point. Now, in this case, datum is given, so you don't need to do anything about datum. But if the datum is not given, you will choose the lowest point of interest as datum. Okay. So I will just make a note here, maybe here on top. Please make this note. If datum is not given, choose the lowest point of interest as datum. Now in this case, which point is the lowest point of interest? B. It is not the bottom of this tank. We are not doing anything with the bottom. So it is always B, which is the lowest point of interest. So even if the datum was not given, we would choose this point as a datum, right? Okay. So from this datum, what is the distance to point A? That is actually ZA. Okay. So for this case, ZA is what? ZA is H. Okay, and what is ZB? The distance between datum and B?
0.
That is 0. Okay, so we have one more term, which is 0. Okay, so let's write it down. What will be 0 plus 0 plus Z GH to BB square to GH. So BB, that is the velocity at B. So QB will be AB Now, as I said, G and AB, you can calculate that very easily. The only problem was to calculate velocity. Now that problem is solved. If you know the total distance between the outlet and inlet, you can actually calculate the velocity for this type of cases. Okay. Are we good up to this point? So in your copy, there are some other examples where you can apply the Bernoulli's equation. I'm not going into details. Those are from your textbook. So please go through the textbook just to have an idea. For this class, what we will do next, we will do the class example 13. So if you don't have class example 13, please collect that from the front row. And just like this one, we will write down the Bernoulli's equation at point of interest, and we will try to find out the value for P, V, and Z. Okay, and we will calculate that. Are we good, everyone? You are done? Okay, so this one was another one, flow around a curved boundary, like if you have an island or something, or some how you can do that. Flow in an open channel. Every case, the condition is there shouldn't be any loss or addition of energy. Okay, a flow in a closed conduit, like it's a pipe. Ventrimeter, we have a ventrimeter in the lab. We will go there maybe on Wednesday or Friday just to see the application of Bernoulli's equation. Okay. Okay, so this is class example 13. So for class example 13, I tried to add two different examples. One is for air, one is for water. So though we said that gases are the compressible one most of the time, if the variation of density is very small, we can consider that as incompressible one. So that's what we will do for class example 13A. But for your class, we will work with class example 13B first, and then we will come back to 13A. Okay. Okay, so let's work on that. Who will read the class example 13B?
The water in an open channel drainage canal flows with a velocity VA equals 4 meters per second into the drainage that crosses a highway embankment. Determine the volumetric discharge through the pipe. Neglect any head losses.
Thank you very much. There is one correction here. If you look at the picture, everything else is in feet and inches. So I will change the velocity into 4 feet per second. Okay. So please change that. That should be 4 feet per second. I mean, you can keep that in meter. You just need to convert that into feet per second. I know you can do that, so that's not a problem. So just change the velocity at a should into feet per second. Okay, so here what we have a highway embankment here. You can see the car like that is going into that direction, and you will see this type of scenario may almost in every road or any residential area also. Like there will be some drainage pipe, they will collect the water from other side to discharge into the opposite side, right? And they usually all these pipe, they are usually buried under the roadway. So here we have that type of scenario, and they are asking you to calculate what will be the volumetry discharge through the pipe. Okay, that means what amount of flow is going inside that pipe. So we have point A is the inlet, right? And B is the what? The outlet. And here we already know for Bernoulli's equation, you have pressure here, you have velocity here, so you kind of know that you have to consider all of those. So for Bernoulli's equation, we know we need to choose a datum also, because datum is not given here. So just from our previous examples, we will choose the lowest point of interest as a datum. So here, which point is the lowest point of interest? The B, right? So that should be the, or like here. Yeah, that should be actually the bottom of 8. I will draw that again. Okay. Now let's write down all the given values. And then we'll write down what values we need to find out. What is the very first given values here? The velocity at A, which is 4 feet per second. Okay. And other than that, I'm not seeing any given values in the question, but I'm seeing lots of dimension in the figure. So we need to calculate something. So for A, we know the velocity. You can calculate the pressure. Also, you can calculate the area. Okay. So what will be the area for A? Pi. That's true. Yeah. So the diameter is 24 inches. That means 2 feet. So 2/2 square, that is the area. Pressure, this time we are not having an open reservoir or something which is open to atmosphere. That A is below something, right? So at this point, what will be the pressure at A? Gamma times H, and H is what here? 3. So that means 62.4 times 3. And since it's pressure, so it will be, I totally forgot what is the unit of pressure. Pound per feet square. Okay, okay, so this is something. Now, what is ZA? The distance between datum and the inlet, what is that? 8. Okay. What is ZB? 0. Okay. What is PB? The water is discharging into open atmosphere. So PB is 0. Okay. Open to atmosphere. Okay. I think those are the given values here. And you need to find the volumetric flow rate through the pipe, which is Q, and through the pipe that should be AB, VB. You know the AB, so you just need to calculate the VB, right? Okay. So, yes.
So just like to make sure this pressure would be zero, like what we have is pressure, not absolute.
Yes, yes, yes. Not the absolute pressure. Yeah. So if when we'll work on the other class example 13a, you will see they mention that you have to work with absolute pressure. That time we will work with absolute pressure. But other than that, we can always work with the gauge pressure. Okay. Okay. So we have given values. We need to know, we know which value we need to find. What is the next step? We need to connect these known and unknowns by an equation, right? So which equation will be the best suited? Oh, one more thing. They said that neglect any head loss. So that is a hint that you can use the Bernoulli's equation because there is no head loss. Okay. So I will just write down that hint that you can use Bernoulli's equation. Okay. So if you are done with this slide, I will move to the next one and I will write down the Bernoulli's equation in between point A and point B. Okay. Everyone's done with this slide. In the back, are you done? Okay. So the solution, apply Bernoulli's equation. In between, we usually apply the Bernoulli's equation in between points of interest. Here we have 2 points A and B. So the equation will be PA rho VA square 2 GZA PB rho PV square 2. And some of you will ask me question in next few seconds or few minutes, what is rho in FPS system? So rho is actually gamma over G. And since it's FPS system, gamma is 62.4, G is 32.2. So you can calculate what will be the rho, right? Okay, so just by having a look on that, ZB is 0, PB is 0. So let's write down those. ZB is 0, PB is 0. And can you calculate the VB from this one? Calculate the VB. I will be here. I will check with you after few minutes. Okay, work on that. If you have the answer, you don't have to announce that. Just show me the answer and I will tell you.
Is A 3 feet below?
Yes, yes, yes. A is 3 feet below the water surface, so the pressure will be gamma times B and gamma. Okay. Work on that. Or you can promise the next one. Work on this last example and answer this one. Gamma. Gamma divided by G. I'm telling you the velocity will be in between 5 and 30. That is the range. The calculation properly should be. Which one would be 4.4. And you want a high value, right? 1.16. $25. Why the G is 1.2? Because that one's good. You're pretty close, but yeah, your equation is correct. Give something in between. Check the calculations. I can't remember the true value, but I can remember the true value.
Yes, also, I'm missing a packet from Friday.
There are some extra packet after yeah, I'm hopefully have, yeah, I have some, but I'm not sure. Anyone else? You slept one day. Okay, so how many of you got something for VB? What answer you got? Yeah, 26.91, that is the correct answer. Some of you may get something different. Most probably you missed something, or rounding issues shouldn't be that much problem here. Still, you should get something close to 26. So let's work on that. So PA is 3 times 62.4. Rho is 62.4 over 32.2. VA is 4 square to 32.2 times 8. And here it's VB square over 2. So if you do the calculation properly, you should get 26 point what? 69? 26.9. Okay. And what will be the unit? Feet per second. And The volumetric flow rate will be what? AB, BB. So pi 2/2 square. And the VB will be 26.9. So what answer you got for this one? 84 or something?
84.6.
Okay, and the unit should be feet cube per second, right? Okay, so the Bernoulli's equation is kind of that much straightforward also. It's just you need to identify the points, and for each point, just make sure if it's open to atmosphere, the pressure will be 0. If it's not, you need to calculate that, okay? So that was for water. Now the next example, 13A, that is for air. And that one is a little bit, it's not tricky, it's just we need to get some values from the appendix A, and we need to check which value should be 0, which value we have something like that, okay? So please complete that, and then I will move to class example 13A. And I'm just thinking, should I start working on that? Okay, we will start working on that. Everyone's done with this one? Any questions so far? Like any confusion or anything? So we are good up to this point? Okay. So let's start working on class example 13A. Okay, and make sure you have your appendix A handy so that you can use that whenever we need that. Okay, can anyone read the question 13A? Thank you very much. Here, the first question you should ask me, ma'am, this is gas. If we want, why we are working on this problem under the Bernoulli's equation. Now, for Bernoulli's equation, we said that for incompressible fluid, most of the time incompressible fluid is liquid, because the definition of incompressible fluid is the density will be constant, right? Now, for gas, like this case, there is no change in, like we are working with a, like just a strip of air or something, and here we are not applying any heat or anything, we are not changing the altitude on and everything. So it's kind of, the density is constant here. So we can compress this problem as incompressible one, okay? And that's why the Bernoulli's equation can be applicable for this case. So just to make sure that for any type of gas, we can't use, like any scenarios of gas, we can't use Bernoulli's equation. We need to evaluate case by case when we can use the Bernoulli's equation, okay? Okay, so for this one, there is an aeroplane which is flying at 80 meters per second in still air, okay? The air is still, at an altitude of 3 kilometers. So from 3 kilometers from the ground level, and determine the absolute stagnation pressure. There are two words we need to make sure we understand. The first one is absolute. So this time we have to work with absolute pressure. The next word is stagnation pressure. Do you know what does stagnation mean, or stagnant mean what? Still. So there is no velocity or something like that, okay? So that will help with this definition. Let's work with that. The given values. Before that, we need to identify what should be the point of interest here. The first point of interest is A, right? And since there asking you to know the pressure at B. So the next point is B, right? Okay. So let's write it down. What are the given values and what values we need to know? What are the given values here? The jet airplane is flying at 80 meters per second. And that point A is actually the velocity at A is 80 meters per second because that is the velocity of that one, right? So VA is 80 meters per second. Okay. At an altitude of 3 kilometers. So what you can do, you can consider that as Z if you want. If you use the datum as ground level, that can be your altitude, or you can use point A as datum also. This is another way.
So is point A a point on the plane? Or just-
Point A, yeah, that is just top, like, what should I say? The most front point of airplane A. Okay, so which one we will use datum? You can use both, either the green one or the blue one. Not the blue one, sorry, green one or the red one. The red? Okay, okay, so we will use this one. The reason you have options here, because A and B, they're in the same level, so it doesn't matter which one you use, they will cancel each other, okay? So in that case, if we use the red one, if we use ground level as datum, the ZA will be what? 3 kilometers, right? Do we know anything else? We know one more thing. It says that the stagnation pressure, stagnant means it's not moving, okay? So that's why the VB will be what? It's not moving relatively, that B. So that means VB is not moving with respect to VA. It's kind of like that. Okay, that's good. So what we will do now, we will apply the Bernoulli's equation in between A and B, and we will try to find out each values, right? Let's do that. If you're done with this slide, I will move to the next one. Are you done, everyone? Okay. So you will need that one at some point. So make this one handy. I will come back to this slide again. Apply Bernoulli's equation in between A and B. So PA gamma P square over two that is the equation, right? Now, as I said, this time we need to work with the absolute pressure. We can't say any pressure is 0 or something like that, right? So we need to work with the absolute pressure. And since it's air, at different level, the pressure can be different, right? And that's when you need to use this one. Which altitude we are working with? 3. So let's just identify that one. Okay. So what is the pressure at 3 kilometer? 70.12 kilopascal, right? And we need to know the density also. What is the density? And you can find that from Appendix A, everyone. Okay. So let's write it down. Absolute pressure at 3 kilometer. Can you tell me what was the pressure again? 70 point? Okay. Density at 0.9092, okay, kg per meter cube, right? Okay, so now you can write down that PA will be 70.12 10 to the power 3.9092. What is VA? VT square. Z is 9.81. And we decided the Z will be what? 12 or, oh, 3, yes. Okay. Equals to PB is the one we are looking for, right? I will just write down stagnation point because that's, or stagnation pressure. The gamma should be 9. Velocity is 0 because that is the stagnation point we decided. And ZB will be exactly same, 9 point. Since you have the same Z, like on both sides, ZZA and GZB, you can cancel those two if you want, or you can keep that. Okay, so what will be the pressure and everything here? Let's cancel these two because they will have like on the same thing on both sides. So we can cancel those. If you don't want to cancel, that's okay also. So give me the number. What number? Let's not cancel that because I think you will be confused at some point. So let's keep that and find out the answer. Okay, what is the number for the first term? So 77, 10 to the power 3, something like that. Okay. Next one. Okay. The next one. You can or you can't, it doesn't matter. So I have decided not to cancel this one so that, because I found sometimes you get confused and you cancel on when you can't cancel something. So let's keep that here. Okay. So what will be the value of this one? So that will be the value on both sides. So
29,430.
29 10 to the power 3, something like that, right? Okay. Now you have only one unknown, which is PB. Calculate that and tell me what number you got. And then I will write down the answer here. I'm just checking what number you should get. Okay. Calculate the PB, absolute pressure. Yes, yes.
No, go ahead. What's the purpose of no, I got like 17,000.
No, the stagnation pressure means this point when something is just not like that. And suddenly when you have solid object, you will stop there. So the velocity is zero. So all the energy is
73,000.
Yeah, the velocity is zero. Yes, yes, yeah. So that's what function.
All right.
Yes.
I got a question. So, what if it says,
Stagnation pressure means when waves go like exact at that point, obviously at that point so everything goes.
if we determine A,
That's why I said you can. Just give me just 1 minute. So, did anyone have any answer?
73.
7. What is the unit? Kilopascal. Yes. So PB should be 73 or this one. Okay. And in next class, I will discuss a little bit about the stagnation pressure because I figured out some of you may have some confusion about that. So we will do that in the next class. And thank you very much for this 1 extra minute. You all have